Hello everybody and welcome to Math 127 at Christopher Newport. Today we're going to continue our discussion about permutations and see how they get used in permutation ciphers. Just as a warning, I'm actually recording this at the same time I'm holding virtual office hours, and so I may get interrupted while I'm doing this, and so if the delivery is a little choppy, that's because I've had to pause and restart a few times, and I apologize in advance for that. Okay, so far, almost all of our crypto systems have relied strongly on modular arithmetic. The only one that kind of isn't directly on modular arithmetic is a Vigenère cipher, but even then, there's kind of a lurking modular arithmetic behind it. Now, permutations, though, they're going to be different. Understand, we've been using arithmetic operations. Permutations are functions, so we're going to be applying them to things. Okay. We're going to look at two types of permutation ciphers. The first is just usually referred to as an elementary permutation cipher. It is the most basic. To do this, we're going to fix a permutation sigma of some length n. So it's going to permute the numbers 1 through n for some fixed n. This is going to be our key. We will then take our plaintext. We're going to break it into blocks of the same length as the permutation. If it doesn't happen to evenly divide, we'll throw some null characters onto the end as needed. And then to get the ciphertext, we take each block and we permute it using sigma. So sigma tells us where to send the first letter, the second letter, the nth letter. So we rearrange them in the order according to sigma, and that gets us our ciphertext. To decrypt it, well, every permutation is invertible. We're going to use the inverse. All right, we take C, we parse it again into blocks of length equal to the length of the permutation. I permute each one of those blocks according to the inverse, and then I should recover the plaintext when I do that. Okay, so let's look at an example. All right, so we're going to encrypt If I'm Gone, Don't Mourn Me with sigma as given there. So 1 goes to 5, 2 to 4, 3 to 3, 4 to 2, 5 to 1. Okay, if you look at it, 1 and 5 get transposed, 2 and 4 get transposed, but 3 remains the same. Okay, so I want to break my plain text into blocks of length 5. The easiest thing to do is to set it up in a rectangular array, and I'm going to have as many columns as I have the length of sigma. So I will put it in my plain text. So if I'm gone, do not mourn me, and I have to throw on a null character, so I've thrown on an X. All right, now I want to permute every block using sigma. Now, the easiest thing to do is to move entire columns at once, because in each block, so 1 goes to 5, so I'm going to move this I to the 5th position. I'm going to move this O to the 5th position, this N to the 5th position, this R to the 5th position. So instead of doing it row by row, I'll just move entire columns at a time. All right, so I'm going to move column 1 to position 5. And similarly, I'm going to take the column in 5 and move it to 1. Column in position 2 will get moved to 4. Column 4 will get moved to position 2. And 3 is going to remain static. It's going to stay right where it is. All right, and so there we go. I've now moved my 5th column over, so GOUX, and then my 4th column, my 3rd column, my 2nd column, my 1st column. Okay, so I then, to get my ciphertext, I read across the rows, and there it is. Decryption basically is the same trick, except we're going to use sigma inverse. Now, sigma inverse in this case turns out to be the same as sigma. Sigma is a self-inverting permutation. That can happen. Okay, so on the other hand, my approach is exactly the same. I'm going to set up I'm going to set up an array, and the number of columns is equal to the length of sigma. All right. Technically, I compute sigma inverse. In this case, I get the same thing back. So I'm going to do the same kind of operation. I'm going to send first column to the fifth column back to the first, 2 and 4 get interchanged, and 3 remains where it is. When I do that, I get my plaintext back, and I parse it back out, and I get on fields of sorrow, and then again, there were about 4 null characters that had to be thrown onto the end. Okay, so in terms of encryption and decryption, permutation ciphers are actually pretty fast. They're really fast with computers, but even if you're doing them by hand, they're not that hard to do. All right, but as always, we don't want to just stop there. We want to figure out how secure these things are. Okay, so let's do some cryptanalysis. All right, so one question that we have to deal with is how to identify when you've received something via a permutation cipher. Can that be ascertained by the attacker? If so, can they then exploit that? Okay, assuming that they know it's a permutation cipher, can they crack it? And if they can crack it, maybe we're going to see there's a new way to attack. So are these things going to be secure in general? Okay, so, let's look at an example. All right, so here we have some ciphertext that's been intercepted. Question is, how do we recognize that it is a permutation cipher? I mean, clearly it's going to be a permutation cipher. That's the whole point of this lecture. But how would we know that? All right, well, let's go back over the tools that we already have and see if any of those can be used. Okay, first option, brute force attack. We just start trying different permutations, slowly increasing the length to see if it eventually starts to unscramble. All right, no, that's not viable. Okay, as we've seen, the number of permutations grows as a factorial. So for short permutations, it's very easy to check, but no one's going to use a short permutation because it's easy to check. So even if it was a length 5, there are 120 options, which by hand would take a while. With a computer, you could do it pretty quickly, but even then, all we'd have to do is go up to a length 10 permutation, and you're at 3.6 million. So brute force is really not going to be an option here. All right, what other tools do we have? Well, if this was a regular class and we were sitting in the classroom, I would stand there and wait for you to think of something that we've used in the past that may or may not be helpful here. Unfortunately, we are not in that situation, so I'm going to have to basically give away the answer. All right, so there are 2 things that we need to consider: the index of coincidence and frequency analysis. All right, these turn out to be very helpful for us. So to see this, let's go to our message. All right, so there is our ciphertext. All right, let's figure out its index of coincidence. All right, and if we do that, not surprisingly, it comes up very large at 0.075 roughly. Okay, so that tells us the cipher would be monoalphabetic. Okay, it's well over the 0.064 threshold. So it's a short piece, so the IC can get kind of skewed a little bit. All right, now, what we might try then, since we know it's monoalphabetic, we might try running a brute add, a brute multiplication, those quick brute force attacks, and we'll quickly realize that none of them work. Okay, so if we were holding on to the idea that it was a classical monoalphabetic, the next thing we would consider would be an affine. Okay, but in order to crack an affine, we need a frequency analysis. So let's do that. Let's take a frequency graph of our message. Okay, let's have a look at what we get. All right, now if it was affine, we would assume most common symbol corresponds to an E, and the second most common symbol corresponds to a T. Okay, and what do we see here? Well, we see that the most common symbol is an E, and the second most common symbol is a T. Okay, so if it's an affine, it sends E to E, T to T. If it were affine, that would mean that it doesn't encrypt it. It just would be regular English. Okay, now, if we look at the message, it is clearly not regular English. So, what does this tell us? Okay, so what have we got? Index of coincidence tells us that it's likely monoalphabetic. We haven't disturbed the frequencies. Frequency analysis tells us that they're stable. It looks like E is going to E, and T goes to T, and a lot of the numbers were the same. So let's compare it to what we think English looks like. Okay, so we haven't used this command before, but in Mathematica, in the MCP particularly, there is a command, ideal graph. All right, and this gives the frequency graph for, in essence, perfect English. Okay, so it should look something like this. This is what idealized English would look like. So E is the most frequent, T is the second, followed by A, O, I, N, and the peaks are relative to each other are accurate, okay? This reflects the fact that E is about 12%, and this reflects the fact that T is about 9%, and then these three come in around 8. So if we compare that graph of idealized English to ours, they're different, but not by much, okay? They've got a lot of the same peaks and a lot of the same valleys. So what that tells us is we're dealing with English, okay? It's got the right number of every character. Its index of coincidence says that it hasn't been changed. Its frequency analysis says that it hasn't been changed. We're looking at English. So this allows us to identify the fact that it's a permutation cipher, because a permutation cipher doesn't change the frequencies of every letter. They remain exactly the same. They just get mixed up. So that tells us that this thing is indeed a permutation cipher. Okay, so with a way to now identify when something is a permutation cipher, now comes the next question. How do we crack it? Okay, well, again, brute force, yeah, no. As I mentioned already, there's just too many permutations. It grows too fast. It would be almost impossible to do by hand. For a reasonably short permutation, even with computational power, I just push the permutation up in size. It's not going to work. All right. Other things we've used, well, we used the frequency analysis. Yeah, but that's not going to tell us anything here. What the frequency analysis tells us is that it's plain English just mixed up. Doesn't tell us how to unmix it. All right. Known plaintext. Known plaintext is devastating. It will destroy a permutation cipher very quickly. Now, unlike, say, the affine cipher where we could use frequency analysis to guess known plaintext, we don't have a means of guessing known plaintext so much. There might be certain instances where we can gather something from intelligence, but there's no sort of mathematical approach that's going to tell us that. All right, but if we do have some, we'll see it's just brutal. All right, and now there's a new attack, and it's called anagramming. All right, so we are going to look first at known plain text, and then we'll do the anagramming attack. Okay, so let's look at this ciphertext. All right, and again, if we were in class, I would ask you if you've got any thoughts. I'm not expecting someone to send me something through the Google Hangout suddenly saying, oh, I know what this is. All right. Looking at it, who knows? All right. On the other hand, if we happen to know it's plain text, then we can figure out what the permutation key is. Okay? So maybe this is part of a longer message, but if I know that the first 3 words turn out to be "you can try," all right, well, I will put down my plain text, I will put down my ciphertext, and I will just start figuring out what happens. Okay, so it is likely, it seems, that 1 goes to 3, so my permutation would send 1 to 3, and then looks like O goes to 4, okay, and then it looks like U goes to 7, and I just keep going and I fix it. All right, and so that gets me what looks to be the permutation key. Okay, so with that done, we look to have the key. All right, sigma would be a permutation of 9 characters, and it would be that. If I had more ciphertext, I could check it and keep going. All right. Now, there's one thing that, if you were paying attention, you might have noticed. There were 2 Y's in the plain text and ciphertext. So 1 goes to 3 as a possibility, but it also could be that 1 goes to 8 and that 9 goes to 3. Okay, yeah, so there's another option. It could be this one. Is that a big deal? Oh no, we have 2 things that we have to check. All right, so if there are letters that repeat, there might be several things to check in a known plain text attack. But again, it's not gonna be much. That's not gonna be hard. So even if there are repeated letters, you're gonna get multiple possible keys, and there's still gonna be significantly fewer than the total number of permutations. All right, so you might have a few that you have to check. Also, it turns out, and we'll see this in another attack, if you've got longer text, you can use the longer text to sort of narrow down the possibilities of earlier versions. If there are repetitions, it can help rule out which one is which. Okay, so now the question is what to do if we don't know the plain text. Okay, so if we don't have a known plain text ciphertext pairing, we rely on something called an anagramming attack. All right, now, what is an anagramming attack? Well, it's kind of like the Vigenère-Koziski attack, where first you try, in the Koziski attack, first we try to figure out the length of the keyword, and then we try to recover the keyword. We're going to do the same kind of thing. We're going to first try to recover the length of the permutation, and then the permutation itself. Okay, now, how do we do this? Unlike Koziski, we have less control over length. Okay, we look at the length of our ciphertext, and we know that that should be divisible by the length of the permutation. Okay, unlike in a Koziski attack where, you could just stop halfway through the keyword. You can't stop halfway through a permutation because it's a function. So whatever the length of my permutation key is, that has to divide the length of the message. Okay, so we look at it, we count how many letters there are, we look at the things that divide it, and then we make a guess. Okay, we guess what the divisor is, we split the text into blocks of that length. And this is where anagramming comes in. Anagram, if you don't remember, is just two words that are the same letters. You just reorder them. We're going to take a block and we're going to reorder it and see if we can make a word. We'll do the same reordering to the next block and the next block. And if it starts to look like we're getting plain text back, we're good. If we aren't getting plain text back, then again, we might need to see if we've chosen poorly. There might be other words we could make. Or our guess for the length of the word is wrong. The length of the permutation is wrong. All right. Something to keep in mind, we're going to take these blocks and we're going to look for words. Words don't have to be contained in a block. They can straddle blocks because it just gets cut wherever it's needed. So there's some finesse required to do this. All right, so here's our message. So let's try this. Okay, turns out if you look at the length of the message, it's 1,300 characters. All right, if we factor 1,300, it's 2 squared times 5 squared times 13. So the divisors of 1,300 is that long list there. Now, keep in mind, the likelihood that it's a 2 or a 4 is highly unlikely. You could brute force those out in no time. Shortest length would be probably 5. I am assuming that I wouldn't give you something with length 1,300. The other thing is that if we're looking at this historically, this was done by hand. You wouldn't want to have permutations of 100 characters long. You're just asking for mistakes to be made. All right, so it's probably somewhere in the 5 to 20 range would be my guess. But now we have to make a guess. Okay, and again, if we were in class, I would make you guess. And then I'd make you all work on it. But we can't do that. So we're going to look at it together. Okay, so we're going to take our ciphertext, and we're going to choose a block length and see what happens. All right. I'm going to start with 5. Okay. The general feeling of, the first example shouldn't be that hard. We'll try that. All right. So what I'm going to do is I'm going to pull a few blocks off. I'm going to take the first 3, I think. And I'm actually going to put them into a spreadsheet. That's kind of the easier way to do this. All right. Now, I don't guarantee that things are going to go nicely and smoothly, and I am allowed to make mistakes as I am trying to do this on the fly. Okay, so here's what we're going to do. We're going to start with this first block here, and we're going to try and make words. Okay, now, to me, the first thing that sort of jumps out is there's the word took. Okay, now it's a permutation, so that uses up 4 of the 5 letters. There's no choice. That one would have to be the G. All right, so I would start with this. And I have to pause. Okay, so I actually had to pause for a little bit and take a call from a student, so I don't exactly remember where I left off a moment ago, but I believe I was saying that we can pull this word out, and then we know that the last character has to be a G because that's the last thing that's left. And so we've seen a reasonably good word come out. This G would be the first letter of some word going in here. Now, the thing that allows this to work, what we do to one group, we do to all the other groups and see what happens. Okay, so first let's have a look at what's going on in terms of the permutation. Okay, so here T is in the second position, so it goes to the first position. So this is saying that 2 goes to 1. All right. The G in the first position goes to 5. All right. Now, K's don't move, so 4 gets mapped to 4. All right, and so now there's a choice because of that repeated O. It could be that 3 goes to 2, and then 5 goes to 3, or 3 could go to 3, and 5 could go to 2. We have 2 options to look at. Okay, well, let's do this one first. 3 goes to 2, and then 5 goes to 3. Okay, so now we look at what this does to the rest of the blocks. All right, so first character goes to the 5th. So O goes here. All right. The second character goes to the 1st. The third character goes to the 2nd. And that's not looking good. Okay. The, where were we? 4th goes to 4. Okay. And then 5 goes to 3. So we get an L there. Okay. That didn't work. All right. We got a good start, took, and then nonsense. Okay. So now, as I said, there were 2 options depending upon the O's. All right. So if we look at the other option, all right. So there, 3 goes to 3. This O goes to there. So that means 5 goes to 2. 4 goes to 4. And 2 still goes to 1. All right. So if we look at what that would do here, you would get RH still. All right. This would still be a U. This would be an O, and that would be an L. Yeah, that still didn't really work. All right. No, wait, something is wrong. Hold on a sec. Let me pause for a moment. Yeah, I screwed up. Okay, so let me just rewrite this here. It'll help me. Okay, so 1 goes to 5 still, so that's going to be an O. 2 goes to 1, so that's going to be an R. 3 goes to 3, so that's going to be an H. 4 goes to 4, so that's going to be a U. And then 5 goes to 2, so that's going to be an L. All right. Again, doesn't look good. All right. So that didn't work. Well, we can be stubborn and we can stick with the decision that it's 5. All right. And we could look for other options for words in here. Now, another option would be 2, okay, as in to such and such. It may also be 2 as in also. But that's going to give us the same start. And this RH and RL would be the same here. That's not good. All right, so let's try that. Okay, So let's assume that it starts with the word got. All right, so what does that tell us? Well, that tells us the G doesn't move. All right, so 1 is going to go to 1 again. In fact, I am going to recopy this just to make it easier to follow. All right, so we're going to assume G-O-T. All right, so 1 goes to 1, 2 goes to 3, and we have this discrepancy with the O's again. All right, so let's assume that 3 goes to 2 for the moment and see what happens. All right, now, why do I want to do that? Because I'm going to see what that does to my other blocks just to start them. All right, so I'm going to get it starting as 1, 3, 2 each time. All right, so this will be O, and then 2 goes to 3, and 3 goes to 2. All right, this will be E, and then this will be T, and this will be P. This will be H. This will be E. This will be O. Okay. Now, yeah, this doesn't look good. Okay, because I've got to begin with, but then I've got to have K-O-O-H-R or something in there make a word, and I don't really see any nice way to make or even start a word I know using those letters. I could put the O first, I could put the K first. It doesn't really help me. So I don't think that's likely. All right. So I did have the choice though on these O's. All right. I sent 3 to 2. I could have sent 5 to 2 instead and gotten a different thing. I could write that out. I'm going to spoil the surprise. It doesn't work. Okay. At this point, it is probably the case that our guess that the length of the permutation is 5 is wrong. So we're going to push the length up. Okay, so I'm going to push the length of the permutation up. I'm going to push it up to 10. That was the next possibility. All right, now we've already seen took. I could still try that again. It's not going to go anywhere. It's just going to get worse. All right, so I want to find something else. Now, the fact that there's a lot of O's really to me implies it is likely there's a double O somewhere in the first word or two. It isn't going to be took from the looks of what happened back up here. If it had been took, this still should have worked out okay, or we could have rescued it somehow, and there really isn't a way to rescue it. All right, so I'm going to pull out a word that I see. All right, now that leaves me with a G. I haven't used the T. I've used that. I still have an O left. I have an R, an H, and a U. Okay. So on its own, it doesn't make a word. But remember, it can straddle blocks. If it starts with look, you look through things. All right. That would be what I would hope for. All right. So let's see what happens. Okay. So the G goes to the 10th position. So 1 gets mapped to 10. T gets mapped to 5, so 2 goes to 5. I'm going to leave the O's for now. There are just too many to worry about. 4 remains the same. All right. 7 remains the same. 8 goes to 6. 9 remains constant. All right. And 10 goes to 1. Okay. Now, I'm going to take that and I'm going to see what happens. All right, now the good news is that in this one, 10 goes to 1, which takes this H and puts it there, which is exactly what I needed to have happen. I needed an H there. That was a possibility as well, but this one will do. All right, so 2 goes to 5. So this 2, so this P gets mapped to here. 4 stays the same. Okay, 7 stays the same. All right, 8 gets mapped to 6. All right, 9 stays the same. And then 10 gets mapped to 1, as we already said. Okay, so this is looking good. So now I want to look at what's left in this block and see if I can make other words, or maybe something that looks like it's most of a word that might continue in the next block, and I can get another block if I need to. All right, so what's left? We have P left, we have a T left, we have an E and an H. All right, well, the E, highly unlikely to go in either of these positions, okay? If it were, it would have to be a word like EYE, but I don't have a Y. It could be T, it could be something else, but seems unlikely. Likewise, it seems unlikely to go here. So I'm guessing this E will go there. Okay, so, wait, sorry. Oh, no, wait. I knew that, sorry. 1 goes to 10. That should have been an E. Okay, even easier. All right, so I've got P, T, and H to fill in. There's an obvious thing. This is a P. All right, so that would mean that 2, wait, 2 goes to 5. This would be, oh, this is the 5. Okay, so this is the P from 5. So 5 goes to 8. All right. And if 5 goes to 8, then O goes to O, which is great. All right, the P is out. And so then I have this T that I haven't mapped, and I have this H that I haven't mapped. But I've got an E, and I've got a T and an H. All right, so this is the H that went here. So 6 goes to 3, and 3 goes to 2. All right, so filling in. All right, and it looks like look through the people. Well, that makes some sense. So let's test it. Okay, so this is what we've gotten. This was the permutation that we just used. All right, and so when we test it, okay, so I made a mistake and showed you the wrong thing. So if I show you the right thing, if we put this in for the deciphering command, we get this, which isn't right. So what's wrong? Well, this isn't quite the permutation. We found the decryption key. We need the encryption key. The encryption key is the inverse of what we found, which is this bad boy here. So if we use this one on the other hand, we will see it decrypts properly. So if we use, again, the perm decipher command, message 1, 10, 3, 6, 4, 2, 8, 7, 5, 9, 1. And there it is. Look through the people and on through the mist to the hill of the headless cross, etc. All right, so there we go. That is an anagramming attack. All right, the anagramming attack will always give you the decryption key. We try to categorize everything in the terms of the encryption key, so you would need to invert whatever you got out. All right, now, as a general rule, permutation ciphers are not tremendously secure. Even if you take a very long permutation, you just have to pick out enough words, do some experimentation, and there are tricks to doing this. You write it on strips of paper, you move them around, and it moves very quickly. So there is a way to increase the security, and this is called a columnar permutation cipher. All right. It starts out the same. All right, I fix my permutation with a length of n. I take my plaintext, I break it into rows of length n. I pad the end of it as I need to. I permute the columns according to sigma. But this is where it's different. I now read down the columns. So it throws kind of like a transpose in there. All right. Decryption works the same way. Divide the total length of the message by n, you write the message into columns of that length, you permute the columns according to sigma inverse, and then you read across the rows. So it adds a little twist right at the end, but that does actually greatly increase the security. All right, so let's look at an example. Let's take this, and we're going to encrypt it with a length 6 permutation. All right, how to do this? Yeah, no. It's just too messy to do as a screencast. I could do it using Mathematica commands, but again, they're more complex Mathematica than you'd ever want to work with. By hand, it's actually not that bad, and I may even actually assign you 1 or 2 in your homework to do by hand, because again, it's not tremendously hard, but sort of formatting it on a screen is going to be difficult. All right, so I am going to leave it there, and this may be the last, or it's the second to last screencast of the semester. I haven't quite decided what we're going to do after the 3rd exam. I don't think there's going to be enough time to introduce more material of any complexity, but we might talk a little bit about super encryption. And super encryption, while cool, doesn't follow nice steps, and I might just do that one by hand. All right, so have fun, folks.